everybody. In this video, we're going to talk about how to Eulerize a graph. So take 3 deep breaths and let's make this math easy. All right, so if we were given a graph like this one, we could use the Euler path and circuit theorem to figure out if it's possible to find an Euler circuit in the graph. So the way that we would do that is we would find the degree of each of the vertices. So I'd say, okay, well, vertex A has degree 2, vertex B has degree 3, and so automatically I already know that there is not an Euler circuit in this graph, because Euler circuits only happen when all the vertices have an even degree. And so because vertex B has an odd degree, that means that it will not be possible to do an Euler circuit in the graph. So the goal of Eulerization is to take a graph that does not have an Euler circuit and change the graph so that it does have an Euler circuit. So the rules for Eulerizing a graph is that you are allowed to duplicate edges that already exist in the graph. So you can't create new edges, but you can duplicate edges that already exist. And so this is an example where we could Eulerize the graph. So the goal of Eulerizing a graph is to change the graph until an Euler circuit exists in the graph. So we know in this one that the way that the graph is currently, there is no Euler circuit because vertex B has degree 3. And since that's an odd number, we automatically know an Euler circuit doesn't exist. So if we Eulerize the graph, we're going to change it slightly until an Euler circuit does exist. And the only thing you're allowed to do during Eulerization is to duplicate edges that already exist in the graph. So you can't create new edges that weren't there before, but you can duplicate edges that already exist. So the process for it is you basically go through and figure out what all of your problem vertices are. So we know that B is a problem because it has an odd degree. It looks like C is fine because it has degree 2. Vertex D is a problem because it has an odd degree of 3. E, it looks like, has 4, so that's fine. F is 4, that's also fine. G is 3, so G is a problem. So is H. I is fine. J is a problem. K is fine. L is fine. M is fine. N is a problem because it's odd. O is a problem. P is a problem. Q and R are fine. So the goal here is we're going to duplicate edges to make it so that all of these odd degree vertices have an even degree. So I might start by duplicating this edge here and creating a second edge between O and P. And if I do that, then O and P now have an even degree because P now has 4 edges and O has 4 edges leaving. So that fixes that problem. I could do the same thing by duplicating the edge between J and N, as well as H and G. And so that fixes all of those issues. However, D and B are not adjacent to each other. Like there's not an edge that connects them. And so I can't just create a new edge because the only allowed action that I can do to Eulerize a graph is to duplicate edges that already exist. And so the way that I'm going to fix the problem that D and B are odd is I'm going to create a path between them. So I could duplicate this edge and duplicate this edge to create a path between them. And that makes it so that B and D have an even degree. And if you notice, it didn't affect the evenness of vertex A. because A originally had 2 edges leaving it and now it has 4, but that's still fine because it's still an even number because the path went into A, but it also went out of A. And so that's the process for Eulerizing a graph, is you basically identify what all of the problem vertices are, or the ones that have an odd degree, because an odd degree vertex will make it so that there isn't an Euler circuit in the graph, and you duplicate edges until all of them have an even degree. So if you want to practice, go ahead and pause this video and practice on this graph, and then restart it to see how I Eulerized it. Okay, so on this one, I'm going to go through all of the vertices and circle the ones that are the problem vertices. So when I look at this vertex right here, it looks like this one is a problem because that has a degree of 5, which is an odd number. This one's just fine because it has a degree 4. This one is a problem because it has degree 5. This one's fine because it has degree 4. This one, it looks like, is a problem because it has degree 5, which is odd, and so does this one. This one is also odd, and so is this one, but that middle one is fine. So I have these 6 different vertices that have an odd degree, and so to Eulerize the graph, I'm going to duplicate edges to make it so that they have an even degree. So for this top one, I think it would be easy to just duplicate this edge, because now both of those will have an even degree. And similarly, I think this edge would be easy to duplicate. So I'll just go ahead and duplicate that. And then for these bottom 2, I could duplicate this curvy edge. Or another possibility I could have also done is I could have duplicated these 2 edges. Either one of those actions would have totally worked. And technically, there's a lot of different ways you could Eulerize this graph. But I'll just keep the Eulerization I did in blue. And so if I were to calculate the degree of each of these vertices now, then all of the degrees would be even, which means on my modified graph or my Eulerized graph, there is an Euler circuit. And so that's how I would Eulerize the graph. And on some of your assignments, you'll also be asked to find an Euler circuit on the graph that you Eulerized. So if that's the case, then you would just use Fleury's algorithm. You know, so like with Fleury's algorithm, you can start on any vertex. So maybe I might start here, and then you just keep on choosing edges to delete, making sure that it doesn't create a disconnected graph. So I might say like, okay, well, I'm going to go along this edge, and then go along this one, and this one, and this one, and this one, this one, this one, this one, and just keep doing this over and over until I've gone through every single edge. And notice that I have to have those duplicated edges, otherwise I would have gotten stuck at some point in my circuit. But because I use those duplicated edges, I'm able to create an Euler circuit. Another topic that you'll see on your assignments is the idea of a minimum cost Eulerization. So if we look at this first graph doesn't have an Euler circuit in it because this vertex, this one, basically those 6 vertices do not have an even degree. And so those are kind of like the problem vertices. And these other graphs show several different Eulerizations that are possible. Because each one of these other graphs have an even degree on all of them. But some of the Eulerizations are more efficient than other ones. Because like if you look at this one right here, this one duplicated 1, 2, 3, 4, 5 edges. This one up here also duplicated 5 edges. But this one was less effective because it duplicated 1, 2, 3, 4, 5, 6, 7 edges. And so the idea of minimum cost Eulerization is finding the cheapest way to Eulerize the graph. Or in other words, finding the minimum number of edges that you need to duplicate in order to Eulerize the graph. And you'll also see a couple problems like this where you have weighted edges. And so in this case, it might not necessarily be the minimum number of edges you're duplicating, but rather the cheapest way that you're duplicating them. So I'll go ahead and do this one as an example. So when I look at this one, this graph does not have an Euler circuit because vertex B and vertex E both have an odd degree. The rest of the vertices are all even, so they're good. And vertex B and E are not directly adjacent to each other. And so instead of just like duplicating a single edge, you're going to have to multiply a couple edges to create a path between them. And there's multiple different paths you could duplicate. Like for example, I could duplicate this one, and then this one, and then this. That would Eulerize the graph. And the cost of that Eulerization would be 18 plus 6 plus 19. So the cost of that Eulerization would be 43. But I could also duplicate this edge, and this one, which would have a cost of 8 plus 15 plus 17, which is 40. So that one would be cheaper. But I could also do this one and this one, which would have a cost of 20, which is way cheaper. And it turns out that the very cheapest way to do it is to go from B to C to D to E, because the cost of that path is 11. And so the way that you find a minimum cost Eulerization if the edges have different weights is you use Dijkstra's algorithm to find the shortest path between your two odd vertices. And sometimes you can just find the shortest path just by like looking at the graph. So like in this case, the graph was pretty simple and it wasn't too hard to find that cheapest path. But sometimes if the graph is more complicated, you may want to use Dijkstra's algorithm to find the shortest path between the vertices. So that's it for this video. If you have any questions, let me know.